Electrical resistivity is an intrinsic property that quantifies how strongly a given material opposes the flow of electric current. A low resistivity indicates a material that readily allows the flow of electric current. Resistivity is commonly represented by the Greek letter Rho. The SI unit of electrical resistivity is the ohmmeter, although other units like ohm centimeter are also in use. As an example, if a 1 meter times 1 meter times 1 meter solid cube of material has sheet contacts on two opposite faces, and the resistance between these contacts is 1 ohm, then the resistivity of the material is 1 ohm. Electrical conductivity or specific conductance is the reciprocal of electrical resistivity, and measures a material's ability to conduct an electric current. It is commonly represented by the Greek letter sigma, but kappa or gamma are also occasionally used. Its SI unit is Siemens per meter and CGSE unit is reciprocal second. The unit of the magnetic diffusivity, in SI, is. Definition. Resistors or conductors with uniform cross-section. Many resistors and conductors have a uniform cross-section with a uniform flow of electric current, and are made of one material. In this case, the electrical resistivity ρ is defined as, where R is the electrical resistance of a uniform specimen of the material as the length of the piece of material, A is the cross-sectional area of the specimen. The reason resistivity is defined this way is that it makes resistivity an intrinsic property, unlike resistance. All copper wires, irrespective of their shape and size, have approximately the same resistivity, but a long, thin copper wire has a much larger resistance than a thick, short copper wire. Every material has its own characteristic resistivity. For example, resistivity of rubber is far larger than copper's. In a hydraulic analogy, passing current through a high-resistivity material is like pushing water through a pipe full of sand, while passing current through a low-resistivity material is like pushing water through an empty pipe. If the pipes are the same size and shape, the pipe full of sand has higher resistance to flow. Resistance, however, is not solely determined by the presence or absence of sand. It also depends on the length and width of the pipe. Short or wide pipes have lower resistance than narrow or long pipes. The above equation can be transposed to get Poilet's law. The resistance of a given material increases with length, but decreases with increasing cross-sectional area. From the above equations, resistivity has SI units of ohmmeter. Other units like ohm cm or ohm inch are also sometimes used. The formula can be used to intuitively understand the meaning of a resistivity value. For example, if an, then the resistance of this element in ohms is numerically equal to the resistivity of the material it is made of in ohm meters. Likewise, a 1 cm material would have a resistance of 1 ohm if contacted on opposite faces of a 1 cm times 1 cm times 1 cm cube. Conductivity sigma is defined as the inverse of resistivity. Conductivity has SI units of Siemens per meter. General definition. The above definition was specific to resistors or conductors with a uniform cross-section, where current flows uniformly through them. A more basic and general definition starts from the fact that an electric field inside a material makes electric current flow. The electrical resistivity ρ is defined as the ratio of the electric field to the density of the current it creates, where ρ is the resistivity of the conducting material, E is the magnitude of the electric field, J is the magnitude of the current density, in which E and J are inside the conductor. Conductivity is the inverse. For example, rubber is a material with large ρ and small sigma, because even a very large electric field in rubber makes almost no current flow through it. On the other hand, copper is a material with small ρ and large sigma, because even a small electric field pulls a lot of current through it. Causes of conductivity. Band theory. Simplified quantum mechanics states that electrons in an atom cannot take on any arbitrary energy value. Rather, the electrons must occupy fixed energy levels, and values between these levels are impossible. When a large number of such allowed energy levels are spaced close together, i.e., have similar energies, we can talk about these energy levels together as an energy band. There can be many such energy bands in a material, depending on the atomic number of electrons, and the distribution. The material's electrons seek to minimize the total energy in the material by going to low energy states. However, the Pauli exclusion principle means that they cannot all go to the lowest state. The electrons instead fill up the band structure starting from the bottom. The characteristic energy level up to which the electrons have filled is called the Fermi level. The position of the Fermi level with respect to the band structure is very important for electrical conduction. Only electrons in energy levels near the Fermi level are free to move around, since the electrons can easily jump among the partially occupied states in that region. In contrast, the low-energy states are rigidly filled with a fixed number of electrons at all times, and the high-energy states are empty of electrons at all times. In metals there are many energy levels near the Fermi level, meaning that there are many electrons available to move. This is what causes the high electronic conductivity in metals. An important part of band theory is that there may be forbidden bands in energy intervals that contain no energy levels. In insulators and semiconductors, the number of electrons happens to be just the right amount to fill a certain integer number of low-energy bands, exactly to the boundary. In this case, the Fermi level falls within a band gap. Since there are no available states near the Fermi level, and the electrons are not freely movable, the electronic conductivity is very low. In metals, a metal consists of a lattice of atoms, each with an outer shell of electrons that freely dissociate from their parent atoms and travel through the lattice. This is also known as a positive ionic lattice. This sea of dissociable electrons allows the metal to conduct electric current. When an electrical potential difference is applied across the metal, the resulting electric field causes electrons to drift towards the positive terminal. The actual drift velocity of electrons is very small, in the order of magnitude of a meter per hour. However, as the electrons are densely packed in the material, the electromagnetic field is propagated through the metal at the speed of light. The mechanism is similar to transfer of momentum of balls in a Newton's cradle. Near room temperatures, metals have resistance. The primary cause of this resistance is the collision of electrons with the atoms that make up the crystal lattice. This acts to scatter electrons and lose their energy on collisions rather than on linear movement through the lattice. Also contributing to resistance in metals with impurities are the resulting imperfections in the lattice. The larger the cross-sectional area of the conductor, the more electrons per unit length are available to carry the current. As a result, the resistance is lower in larger cross-section conductors. The number of scattering events encountered by an electron passing through a material is proportional to the length of the conductor. The longer the conductor, therefore, the higher the resistance. Different materials also affect the resistance. In semiconductors and insulators in metals, the Fermi level lies in the conduction band, giving rise to free conduction electrons. However, in semiconductors the position of the Fermi level is within the band gap, approximately halfway between the conduction band minimum and valence band maximum for intrinsic semiconductors. This means that at 0 Kelvin, there are no free conduction electrons, and the resistance is infinite. However, the resistance continues to decrease as the charge carrier density in the conduction band increases. In extrinsic semiconductors, dopant atoms increase the majority charge carrier concentration by donating electrons to the conduction band or accepting holes in the valence band. For both types of donor or acceptor atoms, increasing dopant density reduces resistance. Hence, highly doped semiconductors behave metallically. At very high temperatures, the contribution of thermally generated carriers dominate over the contribution from dopant atoms, and the resistance decreases exponentially with temperature. In ionic liquids, electrolytes in electrolytes, electrical conduction happens not by band electrons or holes, but by full atomic species traveling, each carrying an electrical charge. The resistivity of ionic liquids varies tremendously by the concentration. While distilled water is almost an insulator, salt water is a reasonable electrical conductor. In biological membranes, currents are carried by ionic salts. Small holes in the membranes, called ion channels, are selective to specific ions and determine the membrane resistance. Superconductivity. The electrical resistivity of a metallic conductor decreases gradually as temperature is lowered. In ordinary conductors, such as copper or silver, this decrease is limited by impurities and other defects. Even near absolute zero, a real sample of a normal conductor shows some resistance. In a superconductor, the resistance drops abruptly to zero when the material is cooled below its critical temperature. An electric current flowing in a loop of superconducting wire can persist indefinitely with no power source. In 1986, researchers discovered that some cuprate perovskite ceramic materials have a critical temperature above 90 K. Such a high transition temperature is theoretically impossible for a conventional superconductor. So the researchers named these conductors high-temperature superconductors. Liquid nitrogen boils at 77 K, facilitating many experiments and applications that are less practical at lower temperatures. In conventional superconductors, electrons are held together in pairs by an attraction mediated by lattice phonons. The best available model of high-temperature superconductivity is still somewhat crude. There is a hypothesis that electron pairing in high-temperature superconductors is mediated by short-range spin waves known as paramanions. Plasmas are very good electrical conductors, and electric potentials play an important role. The potential as it exists on average in the space between charged particles, independent of the question of how it can be measured, is called the plasma potential, or space potential. If an electrode is inserted into a plasma, its potential generally lies considerably below the plasma potential, due to what is termed a Debye sheath. The good electrical conductivity of plasmas makes their electric fields very small. This results in the important concept of quasi-neutrality, which says the density of negative charges is approximately equal to the density of positive charges over large volumes of the plasma. But on the scale of the Debye length there can be charge imbalance. In the special case that double layers are formed, the charge separation can extend some tens of Debye lengths. The magnitude of the potentials and electric fields must be determined by means other than simply finding the net charge density. A common example is to assume that the electrons satisfy the Boltzmann relation. Differentiating this relation provides a means to calculate the electric field from the density. It is possible to produce a plasma that is not quasi-neutral. An electron beam, for example, has only negative charges. The density of a non-neutral plasma must generally be very low, or it must be very small. Otherwise, the repulsive electrostatic force dissipates it. In astrophysical plasmas, Debye screening prevents electric fields from directly affecting the plasma over large distances, i.e., greater than the Debye length. However, the existence of charged particles causes the plasma to generate, and be affected by magnetic fields. This can and does cause extremely complex behavior, such as the generation of plasma double layers, an object that separates charge over a few tens of Debye lengths. The dynamics of plasmas interacting with external and self-generated magnetic fields are studied in the academic discipline of magnetohydrodynamics. Plasma is often called the fourth state of matter after solid, liquids and gases. It is distinct from these and other lower energy states of matter, although it is closely related to the gas phase in that it also has no definite form or volume. It differs in a number of ways, including the following: resistivity and conductivity of various materials. A conductor such as a metal has high conductivity and a low resistivity. An insulator like glass has low conductivity and a high resistivity. The conductivity of a semiconductor is generally intermediate, but varies widely under different conditions, such as exposure of the material to electric fields or specific frequencies of light, and, most important, with temperature and composition of the semiconductor material. The degree of doping in semiconductors makes a large difference in conductivity. To a point, more doping leads to higher conductivity. The conductivity of a solution of water is highly dependent on its concentration of dissolved salts and other chemical species that ionize in the solution. Electrical conductivity of water samples is used as an indicator of how salt-free, ion-free, or impurity-free the sample is. The purer the water, the lower the conductivity. Conductivity measurements in water are often reported as specific conductance, relative to the conductivity of pure water at 7002298150000000025 degrees Celsius. An EC meter is normally used to measure conductivity in a solution. A rough summary is as follows. This table shows the resistivity, conductivity and temperature coefficient of various materials at 20 degrees Celsius. The effective temperature coefficient varies with temperature and purity level of the material. The 20 degrees Celsius value is only an approximation when used at other temperatures. For example, the coefficient becomes lower at higher temperatures for copper, and the value 0.00427 is commonly specified at 7002273149999999990 degrees Celsius. The extremely low resistivity of silver is characteristic of metals. George Gamow tidily summed up to the nature of the metal's dealings with electrons in his science popularizing book 1, 2, 3, Infinity. The metallic substances differ from all other materials by the fact that the outer shells of their atoms are bound rather loosely, and often let one of their electrons go free. When a metal wire is subjected to electric force applied on its opposite ends, these free electrons rush in the direction of the force, thus forming what we call an electric current. More technically, the free electron model gives a basic description of electron flow in metals. Wood is widely regarded as an extremely good insulator, but its resistivity is sensitively dependent on moisture content, with damp wood being a factor of at least 701010000000000000000000000000000000000000000000000000000000000000000000000000000 worse insulator than oven-dry. In any case, a sufficiently high voltage, such as that in lightning strikes or some high-tension power lines, can lead to insulation breakdown and electrocution risk even with apparently dry wood.